Okay, so welcome to class 24. So we have been looking at space groups in the previous class. We said there are 73 symmomorphic space groups, which is just a combination of Bravais lattice with the point group operations, right? And then so I'm trying to look at the entire group of symmetry operations in my crystal across various points, right? So that's the idea of a space group. So that's one way of generating the simpler space groups, which are the symmomorphic space groups. And then we went to the non-symmomorphic space groups, and so one of the operations that we have to understand that gives rise to these non-symmomorphic space groups is what is called a screw axis, right? So screw axis is this 3-1 or 2-1 here, right? So where you're rotating, right? So rotation combined with a rotation operation combined with a sublattice translation, right? So that gives you a sense of a screw sense to your axis, right? So if I have a 3-1 axis, then so it's not just a 3-fold symmetry, but I have a screwed a helical sort of structure in my material, right? So if one asymmetric unit is here, the other one is here, and the other one is here, and so on and so forth, right? So it forms some sort of a chiral structure, right? So with this 3-1 3-2 4-1 4-4 and so on and so forth, right? So along that axis I have some sort of chirality along the axis, right? So I can distinguish whether I have a left-handed system or a right-handed system, right? Okay, so let that be. And then how do you generate space groups? So now I have defined a new operation which is a combination of rotation and sublattice translation, and I combine that with Bravais lattice, and I can make space groups such as P21 21 21, right, or C21 21 21. The underlying system, the crystal system, is still orthorhombic. Okay, but now it is not simply P222 or C222 and so on, but it is P21 21 21, right? So I have all the three screw axes are 2-1 screw axis, right? Or I can have a space group which is just P21. This is monoclinic, right? It's that my two-fold axis is not just a simple two-fold axis, rather there is a screw element to it, so you have to also think of the translation. Okay, so that's now I am going to define what is called an underlying point group. Okay, now so this is very important. I have been using the word underlying point group when I was looking at point groups, but I have never formally defined it. So a space group, right, so such as something like this, right, so I am going to write it as r/tau, I mean, so in the Seeds notation, so what is the operation, what is the space group operation? R/tau operated on any point, any lattice point R, right? So that can generate for me the other points, any asymmetric unit R, any point R. It does not need to be a lattice point, right? So that can generate for me the other points. Okay, so other points where I can put my motif, or so other symmetry points. Okay, so or it can just be an abstract point. I don't need to put anything there. So there can be nothing at that point. It does not need to be a lattice point, but it has the symmetry operations about that point, right? So and then I'm saying what are the other identical points which will have the same symmetry operations. Okay. Now that is I said I apply the matrix R on the vector small r, plus I add a translation vector. Okay. So now the underlying point group of this space group operation is defined as just R of R, right? So no translation, remove the translation. Okay, so this is the underlying point group, right? So now if I have P21 21 21, I am going to remove all the translation operations and say that the underlying point group is just 2 2 2. Okay, if I have something like again C21 21 21, the underlying point group is again 2 2 2. It's the same point group, right? The point group is the same, but I have removed all translational operations, right. So now this is important. I mean, it is not just because I have to define something that I am defining it. This is important because underlying point group is what determines the properties of a crystal, right. Now, the story gets a bit more complicated, so which we will try to address by the end of this class. Now, yeah, so it's okay. So I'll postpone this discussion to the end of this class. But for now, just remember that we have defined an underlying point group where I remove the translation operation from any sort of space group operation, and then I say that the underlying point symmetry operation is 2 to 2 there, or the point group is 2 to 2 there. Okay. So yeah, so I remove the Bravais lattice. I remove all that is related to translation is something that I am removing. Okay. So and then I am defining an underlying point group. Okay. All right. So with that, let's look at, is this the only translation plus rotation operation that I can define? Space group operation, a new operation. This comes only in space groups. It is not there in point groups because there is some sort of translation that is involved, right. So I have, in defining a screw axis, I have defined it as a rotation plus a sublattice translation. Now, okay, so why only rotation? We also have operations which are improper rotations, point symmetry operations which are improper rotations, right. The 1 bar, the 2 bars, 2 bar, let us start with 2 bar, 3 bar, 4 bar, 6 bar, 1 bar. 1 bar is just the inversion operation. Okay. Turns out that if I combine some sort of sublattice translation with so all these things, I mean, we can prove it, but not necessarily in this course. So all these operations are not compatible with sublattice translations, right. So the 1 bar, the 3 bar, the 4 bar, the 6 bar are not compatible with lattice translation, with the translational symmetry upon sublattice, upon combination with, upon combining with sublattice translations. Okay. So it will not form a group, or it is not compatible with translational symmetry. So let us not worry about it, right. So let us not even go into the details of it, right, because so it will take you to a different territory altogether. Whereas what we can we take it as granted in this course is the only improper rotation that can be combined with translation, with the sublattice translation, to yield a space group operation is 2 bar. Now, what is 2 bar? 2 bar is also nothing but mirror or mirror, right. So, 2 bar about an axis is mirror which is perpendicular to that axis. Okay. So, okay. So, then I define what are called the glide operations. Essentially, I have a mirror plane, I mirror my asymmetric unit about the mirror plane, but I do not have a point here, rather I have a point which is translated somewhere else, right. So, this is a translated about a sublattice vector, this is translated, this is the tau vector, right. So, this is the mirror followed by tau, right. Okay. So, this is my seed symbol for a glide operation. So, I mirror and then I glide, right. So, I glide I glide so in using a certain translation vector. Okay. So, I am not going to impose so many conditions on glide. except that I am going to tell you now that so what are the various sort of glide operations that exist. That can exist means that are groups. First of all, if I have this glide operation, I should not affect the mathematical property of a group. I should be compatible with the translational symmetry of the crystal, so on and so forth, right. So all these constraints would tell me that there are only a few glide operations. So I can do what is called an A glide or a B glide or a C glide, right. Now, effectively I have I have a mirror. So, these are what are called axial glides. Okay. So, so let us say I have a mirror about 1 0 0, right, and I have a glide which is my glide vector is 0 half 0, right. So, this is so typically if this is the A axis, right. So, A axis I am just going to draw it as horizontal. So, I have a mirror plane which is like this, right. So, if I have an asymmetric unit here, so this is A, this is B, and out of plane is C, right. So this axis here will be the C axis, right, and this is the B axis. Okay. So, if I have this is A, right. So, this is the 1 0 0. If I have an asymmetric unit here, that asymmetric unit should be mirrored here, right, but it is not exactly here, right. So, I am not actually going to draw it there. So, I am just going to draw it as a dotted circle, that is the mirror position. However, instead of having a mirror position, what I need to have is a glided position. So, glided by how much? Glided by b by 2, half the lattice vector, right. So it is going to be here. Okay. So, this is going to be your glide relation. The mirror is huge, right. So this sort of a relation is your glide relation, axial glide relation. Okay. Like that I can have a mirror plane and I can glide along the mirror plane, right. So that is your axial glide, but I can glide either along, if the mirror plane is about the A axis, then I can either glide about the B axis or the C axis, right. So but I am gliding parallel to the mirror plane, right. So that is the axial glide, right. So the translation vector can either be 0 half 0 or half 0 0 or 0 0 half. So, these are the translation vectors, but typically they should be not along the, not perpendicular to the mirror, not along the direction. If mirror is about 1 0 0, I do not have a glide which is about 1 0 0, rather I have a glide which is about 0 0 1 or 0 1 0, and this is the B glide or C glide. But the magnitude of glide is half the lattice vector, right. So, it is 0 half 0 or half 0 0 and so on and so forth. Okay. So, that is what is called an axial glide, right. For example, I can have a space group which says P PM or so PM is a symmomorphic space group. For a monoclinic crystal, whereas PA, right, where so my two-fold axis is the C axis and I have a glide along the A axis, sorry, I have a glide which is about the A. Okay. So, PA is a non-symmomorphic space group. Okay. My P222 is symmomorphic orthorhombic, P PBCA, right, is my non-symmomorphic space group, right. But I have 3 different glide operations here, right. So, here I have a mirror about A whose so mirror which is perpendicular to the A axis, okay. So, and glide about B by 2 and I am translation about B by 2, okay. So, this means that I have a mirror about B and translation is about C by 2. This means I have mirror about C and translation is about A by 2, okay. So, that is what PBCA means. This is a very standard orthorhombic space group, okay. All right. Now, what else? So, we can have what are called diagonal glide. So, if I have a mirror this way and my axes are this so this is my okay, axis ABC, let us say this is A, this is B and this is C, okay. So, then what I do is I mirror it, but now instead of moving axially either about A or about C, right. So, this is my B this is my B mirror, right. So, this is mirror about 0 1 0, okay. So, whether instead of moving either along A or along C, what I do is I move diagonally, right. So, I move by A plus C by 2. The translation vector is A plus C by 2, whereas mirror is about the B axis or 0 1 0, okay. So, so mirror about 0 1 0 plus sorry and so I am going to represent this operation in seeds notation as follows, translation about half 0 half, okay. So, this is my another glide operation, this is called the N glide or the diagonal glide. Okay. You will see these operations again so in several material systems, right. So, the monoclinic materials and other things. So, N glide is also common. So, you see space groups such as Pn, right. You see space groups such as P if there is a symmomorphic space group is 2 by M and non-symmomorphic space group is 2 by N, right. Whereas, the underlying space group, underlying point group here is still 2 by M, right. So, for both of these the underlying point group is 2 by M. For this the underlying point group UPG is M, right. So, it is just a mirror, okay. So, this is in the monoclinic system. For example, in an orthorhombic system I can have PNMA, right. Now, okay. So, I cannot be using N and N. So, N and M mean the same, right. So, it is called N glide, but so if it is half 0 half I call it N, whereas if it is 0 half half I call it M and so on and so forth, right. So, both of them are diagonal glides. So, if I have a space group such as P where is it, sorry it is in the next page. If I have a space group such as PNMA, I am just going to say that so I have a diagonal glide which is the mirror is the the glide operation means mirror about the A axis or mirror perpendicular to the A axis, and then it is gliding diagonally, which is it is gliding about B plus C by 2. Here the mirror is about B axis and the glide is about A plus C by 2. Here so A plus C by 2, this is B plus C by 2, I am just writing the glide translation vector, and here the glide is just about A by 2, right. So, the mirror is about C, whereas the glide is A by 2, right. So, this is again an orthorhombic space group. And the underlying point group is MMM, right, the holohedral orthorhombic point group. Okay. So, all right. So, that is the diagonal glide. So, after diagonal glide you also have what is called diamond glide. Okay. So, in diamond glide, now it is also possible that the diagonal glide can be a plus b plus c by 2, and this can happen in cubic systems or in tetragonal systems, right. So, this is just an additional information, it is not that we are going to use this fact anywhere else in our course, but so it is not necessary that you should actually move only parallel to the mirror when you have diagonal glide, you can also move in a direction which is along the mirror, right. So, that is also possible, but only in cubic systems or tetragonal systems. Okay. Now, we have what is called diamond glide next, right. So, okay. So, if I before going into diamond glide, if I just have let's write this notation. So, if I have mirror about 0 0 1, right, and the diagonal glide which is about half 0, right, and operated on R. What do I mean by that? I mean that I have a mirror operation which is 1 1 minus 1 0 0 0 0 0 0 about R is nothing but my x y z, right, plus I have half 0, right. So, this is where I am going to put my x prime y prime z prime. Okay. So, mathematically so I can just do this operation, this is the total glide operation. Okay. One glide operation, right. So, like that I have to keep on doing the glide operations to generate the complete so just like I did one rotation, then I said even at that point I have a four-fold axis of symmetry, so I do another rotation operation and so on and so forth until I come back to my original starting point, right. So, that's how I do even the glide operation. So, there is nothing special about it. Okay, fine. So, then we go to the other form of glide operation which is called diamond glide, and here so my my translation vectors are a plus b by 4, right. So, not a plus b by 2, a plus b by 4 or b plus c by 4 or c plus a by 4, or in tetragonal or cubic systems I can also have a plus b plus c by 4. Okay. So, I have a mirror plane here, for example, the c plane is the mirror plane and my diagonal glide which is represented as d, right. So, the diamond glide is represented as d, the diagonal glide is represented as n glide, right. Now, I have made a mistake here in the notation. So, let me correct it. So, M is not a glide, M is just a mirror, right. So, N glide is the diagonal glide is only the N glide. Okay. So, pardon me for that, M is just the mirror operation. Okay. So, irrespective of what is the direction of the glide, right. So, this N glide is so in all the low symmetry crystal systems the N glide is parallel to the mirror plane, right. So, but in the diagonal to the axis, right. So, it is not axial glide, but it is a diagonal glide. Whereas so M in P and MA, right. So, I do not have any translation here, this is not a glide plane, this is just a mirror operation. Okay. So, so let me correct that, I am sorry for that. So, M so for some reason I misspoke that M is glide, M is not glide, M is just a mirror operation. Okay. So, whereas N is a glide operation, right, and A is also a glide operation, N is the diagonal glide, A is the axial glide, right. So, a diamond glide is represented as D, right. So, you will typically see so in all the less symmetric structures, less symmetric crystal systems, I can have a diamond glide which is only parallel to the mirror, right. So, if C axis is if perpendicular to C axis is my mirror plane, then the diamond glide should only be a plus b by 4, which is parallel to the mirror plane. However, in cubic or tetragonal systems, I can have diamond glide which also goes in the plane of the goes perpendicular to the plane of the mirror. So, the diamond glide can also be a plus b plus c by 4, right. So, both of them we call it as diamond glide and represent it with a symbol d, right. Now, for example, right, the most common structures that show diamond glide are what are called diamond cubic structures. Okay. Now, the if I have to write the space group, so what crystallizes in a diamond cubic structure? We have, diamond, of course. Diamond is a crystal of carbon, a solid of carbon atoms. In one of its phase, in the high pressure phase is what is called diamond, right? So it's a very strong material. I think everyone knows what diamond is. The other thing that is also like diamond is silicon, right? So they have exactly the same structure. Structurally, they are the same. Or germanium, right? So germanium solid, right? So all these are cubic structures, right? But they have a diamond glide. I can identify a diamond glide and show you. So I'll try to do that in this class. Or probably in the next class. But so you can see that all these are actually very so these are the platforms on which semiconductors technology, right? So anything that so goes into a silicon fab, a CMOS fab, right, should be somehow compatible with silicon. If I say that I am growing a new material, right, and this new material has brilliant, wonderful properties, but it is I cannot really grow it on silicon, or I cannot really, it is not really compatible with silicon, with combining it with silicon wafers, etc. Then the $1 billion CMOS industry will tell you, okay, then don't bother us, right? So you use it for your properties, you find other applications, but it is not going into my electronic chip, right? So this new materials, for example, I have terbium manganate or something like that, right? Wonderful, multiferroic material or whatever, right? So super properties, right? So so all the properties I can think of are in this, but it is not compatible with silicon, which means I cannot grow it on silicon at reasonable temperatures that are used in the fab, etc. Right? So compatibility is a vague engineering term without so there are some principles that it needs to follow to be compatible with the silicon technology. It's called silicon technology. But if I am unable to grow it on silicon wafers, or if I cannot make it compatible with silicon technology, then terbium manganate can be a beautiful material, but so it is something that the electronics industry will be very hesitant to use, right? So so all of electronics hence is somehow related to silicon, right? So all of the electronics in technology currently, right? So I mean, okay, so I have to take that back, I have to be more precise. All the electronics that goes into your computer chips, for example, right? Not the TV displays and other things, but all the electronics that goes into your computer chips, the transistors that go into your computer chips, etc., are all have some sort of a base which is silicon based, right? So silicon is a very important material that way for your day to day electronics, right? So so we will it's important to actually understand what this crystal is, what is the crystal structure of silicon, right? So especially if we are interested in so the semiconducting technology, right? Germanium also crystallizes exactly the same structure as silicon. Diamond and all these structures are actually called diamond cubic structures, because diamond has that structure. And coincidentally, right? So the space group of all these crystals is actually FD3 bar M. D for a diamond glide, and 3 bar M is the normal point group symmetry, and so F for phase symmetry. And the underlying point group is M3 bar M. Okay. So this is the holohedral point group of a cubic material, etc. So but the underlying point group is M3 bar. Okay. So let us spend some time in trying to actually understand these glides, and so I'm not going into any more details of how to of the space groups, because this is enough for this course for now. What is more important for us are the underlying point groups. So what I'll do now is actually to tell you, right, so how so you can understand space groups by just looking at so there is a book called International Tables of Crystallography. Volume A. Okay, so this is called ITA. Okay, which tells us everything about what the space groups are, right. So right now we will actually see, with this basic introduction of space groups, we will see how to read this book, right. So what are the different notations that exist in this book, and so all our crystals, right, so will have one of these space groups, right. So all the 330 space groups, information about all the 330 space groups is in this, in these tables essentially, right. So we will see what are the different contents of this table and how to understand it from the perspective of what is the crystal structure of the crystal of interest. Okay. So typically, right, so if I have a structure, a material such as calcium carbonate, CaCO3. Okay. Now CaCO3, what I do X-ray diffraction of CaCO3, right. So X-ray diffraction allows me to get the symmetry of the crystal, as well as a lot of details about the crystal, right. So a lot of structural details about the crystal, right. Now I know, so from X-ray diffraction I determine that the symmetry of the crystal is R3C. So C is, I have a glide plane, right. So the underlying point group is still 3m, right, but it is a rhombohedral crystal. I have a threefold axis and I have a glide plane, right. So a C glide, right, so operation. Okay. So it is not a mirror about the twofold axis, but it is a glide about the twofold axis. Okay. About the 2 bar, about the so I am sorry. So it is not a mirror plane, whereas what I have is a glide operation. Okay. So so I can know the lattice parameters. So these are the details that I will have. Then I also, so just by knowing the lattice parameters and symmetry is not enough. I also need to know, right. So I have calcium, I have carbon, and I have oxygen, right. At what positions with respect to a unit cell. So these things determine, the A and C sort of determine for me, and the angles, the rhombohedral crystal system determine for me what the unit cell should look like, right. Whereas in this unit cell I should put the atoms now, right. So by refining an X-ray data, by doing what is called rate field refinement, I can get the positions of calcium. Calcium is at what is called 6b position. I do not understand what this is right now. With respect to this is what is called a Wyckoff position. We will look at what Wyckoff position means. It tells me about something about the symmetry of that point, right, and that point with respect to the unit cell is 0 0 0. So I am going to place calciums at 0 0 positions of my rhombohedral unit cell. I am going to place carbon at 0 0 1/4, but however so I have 6 such positions, and this has a symmetry, this has a Wyckoff position which is called A Wyckoff position. But what does it mean? A Wyckoff position tells me something about the symmetry of that point. Okay. Similarly, I have oxygen at so any x 0 1/4, right. So okay, so x is precisely here 0.257, right. So this is not a very nice number, right. So it is not 0.25, it is not 1/4 the length of the unit cell, but it is some 257 of the unit cell. Okay. So it is not a very nice number, which means this oxygen has distorted a bit. Okay. So looking at this sort of a data, I know everything about my crystal, right. So essentially I need to know the symmetry, right. I need to know where my atoms are positioned and how can I reproduce all these atoms, right. So using these symmetry operations, and I need to know the unit cell parameters, right. So using, if all this data is there, I will know everything about my crystal. In fact, in Vesta, right, so we are trying to visualize many crystals, right. So what I do is I download a file called crystallography information file, right. So from the databases. Now crystallography information file has all this information in it, right. So, and this information is fed into Vesta, and then I can actually make a unit cell, I can multiply it, I can visualize the unit cells, etc. Okay. So this is the information we are seeking for. Okay. Now let us come to these tables, right. So what does international tables of crystallography consist of, right. So let us look at a space group P4 by M. Okay. Now P4 by M, the number of this space group is 83 among 230, right. So I have 230 different space groups. So every space group is given a number, right. So it actually starts from low symmetry space groups. It starts from a triclinic space group, which will be 1, P1 will be 1, for example, number of the space group of P1 will be 1, and it moves, it goes up in symmetry, right. So as this number keeps increasing. Okay. Now let us not worry about what Patterson symmetry is initially, because Patterson symmetry has got something to do with X-ray diffraction that we didn't do in this course. Whereas so okay, what is the crystal system? Crystal system is tetragonal. This is easy to understand. Okay. Now this sort of a thing we just looked at, right. So what are the various, so what is the unit cell? The unit cell is a primitive unit cell. So these are my lattice points, right. And I am going to say that so about every lattice point I have a symmetry which is 4 by M, right. So I am going to select my center, my origin at one of these lattice points, right. So this is my lattice point, which is the origin, right. And so then I am going to define all the symmetry operations. So this here I am going to say that okay, so I have a 4 bar yeah, so I have 4 by M. Okay, so I have a 4 by M here. So I have two mirror planes here, and I have so this is my 4-fold axis. I have a 4 by M here, I have a 4 by M here, I have a 4 by M here, and so on and so forth. But accidentally I am also generating something which is not a lattice point, which also has 4 by M. We saw this earlier, right. So when we are looking at space groups, so this is the representation of all the symmetry elements in your unit cell, and this is the representation of all the symmetry operations in your unit cell. Okay, symmetry operations in unit cell. And this is the representation of all the asymmetric units and their stereographic projections. About the lattice points. So you are combining both lattice points and their stereographic projections, right. So that's this figure, right. So looking at this figure, we understand what are the different sort of symmetry operations that exist. Okay. Now we have what is called an asymmetric unit. Now asymmetric unit is that volume of the unit cell, right. So which is independent, so if I know the asymmetric unit, if I know that okay, so asymmetric unit is 0 less than x less than half, 0 less than y less than half, 0 less than z less than half. So 1/8 of the unit cell here is my asymmetric unit, right. So if I have a unit cell which is somewhat like this, right. So I am going to say that it's enough to know, so if it's enough to place one of my asymmetric units in 1/8 of this unit cell, and my symmetry operations will make sure that this unit is repeated everywhere else, right. So the basic minimum unit, right, that I need to have, that will be repeated by my symmetry operations as well as lattice translation, right. So that is what is called an asymmetric unit, right. So typically asymmetric unit is a volume, but inside the asymmetric unit is so volume which is defined as 0 less than x less than half, 0 less than y less than half. So it is, so this notation gives us the volume of in a part of the unit cell. But I can have some sort of an atom there, and then I can say that okay, so this is my asymmetric unit, and this asymmetric unit is being repeated, right. So based on the symmetry operations, so I am repeating, I have to make sure that this asymmetric unit follows the symmetry of the crystal. Okay, so I have to repeat it accordingly, okay, based on the symmetry of the crystal. Okay. Now this is a space group, right. So since it is a space group, I have many points about which I can have many sort of symmetry operations, right, point symmetry operations. Now So the first point about so what are all the different symmetry operations I have? I have 1, I have 1 bar. So I have an inversion symmetry here. I have a mirror, I have 2-fold, I have 4-fold, I have 4 bar axis of symmetry, and so on and so forth. In fact, this is a 4 bar axis of symmetry. Okay, so it's not just 4 by m, but it is a 4 bar axis of symmetry. Okay, all right. So then, I mean, so 4 by m is much higher symmetry than 4 bar. Okay, so that you can actually prove to yourself. So what is this that so generators, you don't need to worry too much about what are the generators, but we what is important are the positions, right. So now here if you see, right, so I am actually positioning all my symmetry operations from so all the different points, right, I am actually labeling them from 1 to 8, right. 1 being all those positions which have the highest symmetry, right, and the highest symmetry is 4 by m. Okay, 4 by m is the highest symmetry, and then there is a position A which is 0 0 0, there is a position B which is 0 0 half, there is a position C which is half half 0, and there is a position D which is half half half. All these points have a 4 by m symmetry, 4 by m point group operation, right. So operating through them, okay, all A B C D, right. So all the so the 1 positions are positions of highest symmetry, and their Wyckoff symbols, right. So Wyckoff symbols, so this is what is called a Wyckoff symbol. Wyckoff symbol A represents a point in your crystal that has the highest symmetry. Okay, so in this case A, B, C, D, all of them have equal symmetry, right. So equally high symmetry, right. So that's okay. So I keep on so I say A, B, C, D, E, F, G, H. If I say I have to place my atom at a Wyckoff position G, that probably means that the point where I am placing that atom has a very low symmetry, right. So very low point group operations, right. So very low number of point group operations, that is what is meant by low symmetry. Okay, so then I my second Wyckoff position has so these positions E, F have a symmetry 2 by m, positions G, H have a symmetry of 4, both of them have equal number of symmetry operations. That is why I just represent it as oh sorry, this is the multiplicity, this is so I have 2 such E positions, right. So one is 0 half 0 half 0 0. I have 2 such F positions which is 0 half half and half 0 half, and so on and so forth. This is a monoclinic system, right. So the multiplicity tells me that so because of 2-fold symmetry, if I have a 2-fold symmetry at 0 half 0, I should have the same 2-fold symmetry at half 0 0, right. So because my C axis is 2-fold axis of symmetry. Okay, so and so on and so forth, right. So I have 2 different positions, the multiplicity is 2 of the position F. F tells me what is the Wyckoff position, and Wyckoff position tells me so that this is less symmetric than A, but still it has a symmetry operation which is 2 by m, right. So about the F point I have a 2 by m symmetry, and an F point in P 4 by m is actually 0 half 0 half 0 0, right, with respect to the origin which is 0 0 0. Okay. Similarly, the G point has even less symmetry, that is actually 0 0 Z. So here it is not a single unique point, right. So the G is not a it is an axis essentially, right. So any point about 0 0 Z has a 4-fold axis, right. So right, so I don't need to precisely define Z, I can go to any Z, but I have to be on the 0 0 axis, right. So then I have a 4-fold axis of symmetry, right. So these are all the point group operations that I have, and so the one which is just an identity operation exists about any point, right. And this point is so if I have x, y, z, the same is the environment about x bar, y bar, z by symmetry. So it will have a multiplicity of 8, right. So I can x, y, z is equivalent to 8 different points, and each of these points, any point, right. So each of these points has a trivial symmetry which is a 1-fold symmetry, right. So that is how you read the tables. Okay. Okay, so then we have what are called subgroups and supergroups, but so we don't need to worry too much about them right now. Okay, so essentially subgroup is, if I have a group, it's like a subset, right. So and a subgroup all the elements of the subgroup are in the group, right. So it is like a subset of a group, right, and maximal subgroup. Okay, so let's not go into the discussion of groups and subgroups right now. So we will get back to this when we do what are called phase transitions. Okay, so for example, P4MM is a subgroup of PM3 bar M, right. So there are more symmetry operations here, including the 1 bar operation. 1 bar is an inversion symmetry, right, whereas there are less number of symmetry operations here. This is a polar group, but all the so this has 4 mm, this has and so on and so forth, if I list it out, right. So here there are less number of symmetry operations, but turns out that so all the symmetry operations that are here are included in this. Okay. So this is a subgroup of PM3 bar M, right. So in fact we have come so when we are doing barium titanate, we said that this is the high temperature phase or more symmetric phase where there is inversion symmetry, and this is the low temperature phase, there is no inversion symmetry, or this is polar, right. So so you can see that they have a group to subgroup relation. So typically phase transitions, not always, but what are called second order phase transitions, so a material, when it is transforming from a high symmetry phase to a low symmetry phase, it goes from a symmetry a certain space group to its subgroup, right. So subgroup has less number of symmetry elements, but it is still so you have to just kill some of the symmetry elements to undergo that phase transition. So the group subgroup relations become important in the context of phase transitions. Okay. So similarly P4 by N, so instead of M I have a glide operation here. So here I can define my origin, right. So my origin at 4 bar on N, so this is at some position which is here, and so with respect to that you can know all the symmetry operations that exist, what is the asymmetric unit, right, and what are the different Wyckoff symbols. So here I have 4 bars about A, B, the multiplicity is 2, I have 1 bar, so I have a in 4 by N I have an inversion symmetry, right. So 1 bar about all these positions, right, and all these positions, right. So there are all these points about which there is an inversion symmetry, right, and I have a two-fold operation, I have an identity operation, right. So as I keep on reducing the symmetry, the number of points that can have this symmetry increases, right. So any XYZ in this crystal can have a one-fold symmetry, but this XYZ is the same as just by the other 4 by N symmetries. I will have 8 such positions which will have which are identical, right. So the multiplicity of the G position is 8 hence. Okay. So I have so by virtue of the 4 by N symmetry I have 0 0 0 which is identical to half 0, right. So whether I say 0 0 0 or whether I say half 0, it is exactly the same in this space group, in this crystal with such a space group. Okay. So yeah, so that's what this is. Okay. All right. So then I have subgroups and supergroups which exist, and these are the conditions. If you did some X-ray diffraction, you know that so there are some forbidden conditions for diffraction to occur or diffraction not to occur from this crystal. Okay. So this is a general framework of how you read the crystallographic tables. Okay. So with that, I think we will conclude it here, and tomorrow or in the next class we are actually going to look at certain structures of importance, right, so which keep on coming all the time, and we will try to visualize it with Vesta software. Okay. So we will start with silicon, we will start reducing symmetry, and then we will see what are called the zinc blend structures, which we have already seen, and then we will see the analog of zinc blend in trigonal systems, which are called the Woodside structures, right. So all these are important, and we will also look at their technology, their importance in terms of property. Let me not use words like technology here, because let's first try to understand the science behind these materials. Okay. All right. So with that, let's meet again in the next class. Thank you very much.